So this is the second part of soil for today. So after seeing Norbert's presentation about the future of soil, this one will be a presentation about the current situation and really the version that you can download now, and I will show a bit how to use it and show a bit at the end of what is the direct next step for the next version. So what is soil? As we already saw in the first talk, soil is an object-oriented database that is implemented in Faro. Object-oriented database means it actually does support transactions. It is implemented using the MVCC pattern, so this model, multiple version concurrency control, multi-version concurrency control, which means that when soil writes something to disk, it is an append-only strategy. So it will never overwrite any data on disk, but it will just append. And if you want to clean up because it gets too large, there is a GC that you can use to clean up, which then allows you, of course, to not clean up everything, but keep some, and you can implement your own strategies as you like. Another component which is very important is the indexing. So we do have an indexing system, and we will see an example towards the end, which implements both a skipped list version and a B+3 version. And the goal of soil is to have a simple yet powerful database that makes it easy to develop with, but that makes it easy to develop soil itself too. So one of the most important properties of soil, and one of the reasons why it was developed, is that it does not need any external database. So contrary to all the other libraries like Voyage, for example, it does not rely on another process which is the database, but it actually is a self-contained library inside of Faro that implements the database. And as I said, multi-version concurrency control, data is never changed. Soil is actually astonishingly small. I think I might even have, yeah, so the version that we use for the tutorial is version 2, but we actually today released version 3, so the mail will be out today, I guess. And so my first slide said 120 classes, 1,700 methods, 6,000 lines of code. It got a little bit bigger with the features that we added, but not much. I was actually quite happy after doing it again because I feared a bit that it would be more, but it's actually not much more. So maybe 1,500 lines of code more and almost just 15 classes more or something like that. So actually kind of nice. As you can see, there are two parts. There is soil itself, which is the model, transactions, and the indexing. And especially because of the indexing, this is nearly 7,000 lines of code. And then there's a serializer, which is a simple yet complete serializer for any Smalltalk object, or for any Faro object. And that one is just 1,200 lines of code, which is quite nice. So why soil? Why was this developed? So the main driver was Norbert, who was already had already a version of ActiveGrid running using Voyage, and he was not very happy with that. And so he said, we need something better. And I came in because I actually think that it would be interesting for Faro itself, and I will have a slide after that explains that a bit. So ActiveGrid, I think it's interesting to explain a bit what it is. So it's a platform to automatize, solve problems for small companies. The idea is, the central idea is that you have data in grids, like in tables. Then you can define forms to get data into these tables. You can define views on the data, like a Kanban view or a map view, or things like that. Then you can define workflows so that you can do actions when something happens. And the newest components is a web view so that you can actually show the data in a nice way directly without needing to create another website. And here I show an example, which is a new companies that use Smalltalk application that I implemented, which already, the form is already linked on ESUG.org, but the view is not yet live because there's almost no data inside, as you can see. So there's Nuri added his company. I added AptiveGrid as a test with the wrong email address. And then it's one company that added actually information via the form already. But I will send the link around and you can actually add your company, because you can see here the view that the system provides. I want to actually render the view like that on the ESUG website so that it comes directly out of the database. And with the workflows, we can actually then do interesting stuff. So I can actually, when you subscribe your company, you will get a link that allows you to edit your data, which is very important. And we can, every year, we can send a mail like, hello, please update your data, because right now the list of companies on the ESUG website is very out of date, and we have no contact information, we know nothing. And this one, I think, will improve it a lot. I will show this in the Show Us Your project a little bit, how this looks like live. Because this talk is about the underlying system, and that is soil, which actually stores all these things on disk. So the workflows, the pages, the table, all of these are Faro objects, and soil serializes all of them. And all the indexing is done using soil so that you can actually do things fast. What I'm interested in is actually a research component of it. One research direction is, if you look at Faro and some of the problems we have, then you can actually think that they are database problems. So we do have the sources and changes mechanism and epicea, and they are actually not that nice. So for example, the reading from the sources is really slow because, yes, we have an offset to a text file, but then it's just a text file, so it needs to actually pass to find the end of the text, which is really slow. If you do send us off, it iterates over all methods and all literals to find the sent message, with the problem that if you have code that is actually not in the source code, it will find it too. So if you have an if empty, then it's actually compiled as is empty if true, and that means that if you search for senders of is empty, you will find lots of methods where there is no is empty, things like that. And the only way to improve that is, I think, indexing. So that means indexing, the database indexing is something that would be really helpful for Faro, the IDE. Another thing is code history. It would be very nice to have a better history model directly in the image, to not rely on parsing from GitHub. Another thing that I'm interested in is transactional change. So you see transactional change in Faro in many places, but it's very ad hoc. And so the question is, can we not do that better? If you want to play with soil, you can easily install it. So I put on the slides all the information that you can do it yourself. You can try it, but I did not prepare it as like an interactive thing that I would wait for you, because I think that is too slow to do as part of the presentation. But everything is online, and even the code that I will use for the bigger example, I will put that on GitHub later so that you can load it, and I will update the slides. So soil actually supports version 11 to 14, and we have CI running that makes sure that it actually is green on all of those platforms. You should not use the main branch because it's under active development, and especially now it's not a good idea because we plan a breaking change of database format between version 3 and version 4. Which means not breaking really for you, because there will be, of course, migration possible, but it will not be a seamless migration like until now. So using the main branch is only possible for experiments, and it might be broken, so you take care. I will use in this tutorial version 2. I think it should all work with version 3. I will test it at some point, but I didn't find the energy to test it now after the release was officially done. So load version 2 for this tutorial now. So what can you do with soil after you loaded the code? So the first thing that you need to do with soil is that you need to open the database. So the idea of soil is that there can be many databases. A database is a directory on disk, and you can open many of them. If you look at AptiveGrid, for example, it has one database per customer. And that is a good strategy to use with soil to use many databases. So the idea is not to have one big database, but to use many independent databases. And the idea is that you give a path, which is relatively to the image, and then you need to initialize the file system once, which puts all the structures there, and then you can use it. You can either do it in 2 steps or in 1 step. And if you, at the end of your usage, you need to close the database. If you want to get rid of the database, you can either do that just deleting the directory, of course, or you can do it programmatically using destroy. The reason why we have that in the image is testing. So if you look at the soil tests, and if you look at my examples in this talk, we will always create a new soil, and then with a path, and then we say destroy to get rid of the old one. Because if you have a test, of course, the old test did create a database, and you want to keep it actually on this because you might want to look at the database after the test finishes. So you don't want to delete it while with running the test, but you want to delete it before running the test again. So and that's a pattern that's quite nice. That's why initialize file system is independently there. That's why destroy exists from within the image. Now we will actually do a really small full round trip of storing something in soil. I will first explain it, and then I will do it in my image. So as soil is transaction-based, the very first thing that we need to do is that we need to create a transaction. So as we have created soil, so the reason we opened the database, we assigned it to a variable. The reason for that is that we want to talk to soil to create transactions in many cases, in most cases. So we ask for a new transaction. Then we can actually store the root of our object graph that we want to store. We can assign it to the root of our transaction. And if we commit, then it will write that to disk. And the complete code, of course, needs both the creation of the database and then the creation of transaction, storing it. And we can actually try that in Faro itself. So I have here a Faro with the first playground, which has the simple example. So we actually execute this. This gets rid of the old database that I created last time I tried that this still works. And now soil is the instance of the database, which is there. And we can create a new transaction. We can set the root to a point. As we can store any object, that's perfectly possible. I use a point because I want to store something where I can that I can change, and I can show you that I can change the object and store it again. And if we now do commit, it actually writes it to disk, and it's in the database. And I could now close the database, reopen it, but not reinitializing, of course. And then I could get it from there. Or I can reuse the currently open database to get it back, which we will do as a next step. So if we want to get it out, it's exactly the same idea first. So we first need to create a transaction. And then we can access the root of the object graph to read back whatever we put there. You see yourself here, and the reason is that when we do that in the image, so let's do the new transaction. If we just do this and print it, now printing works fine, but inspecting, now inspecting the second time works too. So the thing is that it actually that you actually get back first a proxy, but in that case not. I don't know why. So the idea is that all the roots. So I think maybe the inspector already instantiates the proxy correctly, so which is nice. But the thing is that you get back a proxy because every the root object will not be loaded immediately, but you will get a proxy back, and then when you do something with it, it will load on demand the object. So in our case, we get back 5 plus 2. And as we didn't change anything, we can also say transaction abort, and we are done. So if you want to change something, You need to do it, of course, in a transaction. That's the main reason why we have a transaction, that if two people change something, that they do not conflict. So again, we create a new transaction. And in this case, we would, as we have a point in our root, we use set x, set y to change the point. And in the current version of Soil, we need to actually tell the transaction if we changed a subgraph so that it knows that it has to commit. I will discuss at the end that this will go away. So this is an intermediate need, which can make the use a bit annoying. Sometimes that's why it will disappear in version 4, I guess. So we mark dirty the object that we changed, and then we commit the transaction, and then we can read it back. So let's try that in Faro. So we have again, we say transaction, new transaction, then we, if we look here, we have 5.2. If we set it to 2.2, we mark it dirty and we commit. Then if we would read it back in another transaction, new transaction, we get back 2 at 2 instead of 5. So we have a full round trip shown. So we stored something in the database, we committed it to disk, then we changed it, we committed the change to disk, and we read back the change, and it works. Of course, this example is extremely trivial. I mean, a point is nothing special and a bit useless, but as it's an object like any other object, and you have seen that it stores the point and the two integers inside, this is already a full object graph that we stored. And Soil actually stores the full reachable graph of your model that you put as a root. This, of course, means that you need to be able to control where you want to stop storing it. And for that, we have there is the possibility to override a method on the class side, Soil transient instVars, which returns an array with the names of all instance variables that you want to not follow on the traversal of your storage. So if you have an instance variable that makes no sense to be in the database, or if you hold on to something huge in the image that you really don't want to store in the database, then you should implement this method to not store that subgraph in the database. So this is control number 1. And the other control is partitioning. So we said that we store the whole object subgraph that we assign to the root in the database. But imagine that would be a bit useless. Imagine you have your model of your application with all the data inside. It would mean that if you access the root, that it would load all this graph back into memory, which is, of course, not what you want. I mean, the whole point of a database is that a lot of data is on disk, and you can access parts of it and not everything, so that you can actually access the model root, but you do not load the whole model into memory, but only a part of it, enough so that you can discover other parts that you then load on demand later. And for that, we have the possibility to actually denote any object in the graph as a root object. And that happens by just saying transaction make root this object, and then when the graph is loaded, it actually stops at that point, and it puts a proxy there. When you access the proxy knows how to ask the database for the next subgraph, and it will then load that part into memory, which again might have roots defined where it stops loading, and then only on access it will continue to load. And this allows us to actually use this very simple model as a real database where you store your whole model, but you can actually get only parts of it out without having to load everything back. one example that uses this feature is actually a specialized dictionary. So imagine you would put as your model root a dictionary, which is actually something that can be useful. What would happen if it gets loaded back? It would actually load the whole dictionary back and all objects that are the keys and all values if you don't manually make them roots, which is actually not what you want if the dictionary gets even moderately size. So solid persistent dictionary is a dictionary that, for one, automatically makes every value a root, and the serialization is implemented that it loads into memory all the keys when you deserializes, and it does not, and because the values are roots, it just puts proxies for all the values. And that means that you can load the full dictionary kind of by just loading the keys into memory, and then all the values are lazily loaded when you access the dictionary. You can just create it like that, and it's just compatible with dictionary, and you can just use it like a dictionary. This is interesting because we will use that in our slightly more complex use case of soil in the next example. For that example, I actually hired the heroes from the Voyage tutorial who were really happy to join. It's a very simple example. So we have a class hero with name, levels, which we don't use, and the powers that the hero has. And the power is actually just an object with a name. And I can show that in the image. So I have a browser somewhere where we see, yeah, power is just name with successor, and hero is just name, level, which we don't use in our example. And then it has add powers, and powers is lazily a set. And that is a fairly simple but more usable example to show a little bit of what to do or what is possible. So what we can do now is we can instantiate some heroes. So I instantiated 2 with some powers. And as you can see, thankfully, they do not share the same power. This simplifies indexing. So in our example is 2 heroes never have the same power. But of course, we could improve it to do that too. So what we do is we just make an array with 2 heroes that have some powers. And then we do, again, what we already saw at the beginning. We create a new soil database, and again, we do the destroy initial file system so that we can actually execute in the playground this code multiple times and always getting a clean database for testing. You would, of course, not do that in your application. There you want to keep the database. And then what we do now is that the root, we put a persistent dictionary. This is for the example a dictionary. You could flesh out the example, and you could have a hero manager or a hero model and store that. But for our small example, a persistent dictionary is nice. So we, for now, just add one entry into it where we put the heroes as under the key heroes, and we save it to disk. And that works, of course, exactly like that. So let's close this. Let's go here. So we, again, reinitialize the database. Then we create our heroes array. We create the persistent dictionary. Then we store that we store the heroes inside there. Then we create a new transaction. We store our dictionary there. And then we commit, and with that, the heroes are now stored on disk, and we can reload them as we want. So, for example, we do that here. We do a no transaction. If we now do that, then we can get back the array with the heroes as we would expect after seeing the simple example. Exactly so. And yeah, I have the code here in the slides too, so for everyone to do it at home. I will store, I think, the minimal hero model on GitHub too, and I will put, I think, the code into the slides too in a later point. So for the version for people at home, it's so simple that I think it even makes sense to just create the classes yourself and not load them from GitHub. So now we still have the problem that even so we now load lazily, I mean, we still load all heroes. We could now add the heroes into a persistent dictionary too, so that by name, and then you could check for one, and you would only get the one lazily loaded. But that really doesn't solve too many problems yet, because imagine you want to find now all heroes with a certain power. That would mean you would need to load all heroes from disk, iterate over them standard, and get back the heroes, and that defeats the whole point of a database, because the idea of a database is that we have data on disk that we do not need to load into memory, but that stays on disk. But we still can find the data that we are interested in. And for that, we have indexing. For now, our indexing, for one, it has the idea that an index is a dictionary, which means it is key to one value. So if we would extend our heroes with the same power multiple times, then we would need to store a collection. We don't need that now, so it's a simpler model for our heroes. So we have two versions of the index dictionary. One is a B tree and one is a skip list. The skip list is used in production. The soil B tree not yet, but it should be production ready. So all tests are green and it works nicely. So the soil index dictionary is, as I said, key to value, but the key is a bit special. So it's not a key like in a standard dictionary, because the key has to be mappable to a number. So actually, it's a number encoded as a byte array. It has to be sortable, so that means it is sorted by this number. So if you take the key, it's a sorted dictionary sorted by the number, by the order of the keys. And the keys have a defined size. So that means, I mean, you can ask for this soil index key for any object, but if your string is very long, for example, then you will get a long key, and you need to actually set up your dictionary with the correct length. So it's a bit different than what you would expect from a standard dictionary, because it's not a dictionary, it's an index. What is the same like in a dictionary is that the value can be any object. And if it's an object in the database and it's actually is not stored another time, it is just in the database once. So you can find a database, you can put as a value an object that is already in the database, and this way, if you ask for the key, you get back this object that is in the database that you're looking for. Behind it, there is a low-level implementation. So the actual B tree and skip list index is actually lower level. So it's actually really binary key to object ID. That's why it can be any object in the database, because the value is an object ID. And that's why it is constrained for the key, because it's a binary sortable key that is stored there. What is interesting is that because it's sortable, it's a sorted dictionary, and that means that you can iterate over it in order of your key order very easily. And that's quite useful, because that means that you can look for something and then ask for the next 20 entries in order of the sort order that you defined. So if you use a string, that means that you can really, in alphabetic order, get stuff out of your index, or whatever the order is. So you can make a geo-index and you get like stuff that's close to you, for example. What is interesting is that the index lives on disk. We store right now in 4 kilobyte pages. And that means, for one, that you can make as many indexes as you want. They don't take main memory. They are in the database. They're on disk. And it loads on demand only the pages that it needs to find the key. So for the B tree, that means that it really just loads like 2, 3, 4 pages, even in a huge dictionary, because 4 kilobyte pages means lots of key value, lots of index entries, and this scales quite fast to really big numbers. The reason why you can actually walk through in order is that the data pages are actually concatenated in one direction, so you can actually follow the next, you can get the next values easily, which is nice if you want to actually show in your UI a page and you have a next button. It would really just fetch the next values using this. No need to load the whole index. What we do here now is that we want to have an index from the name of the power to the hero that has this power. And for doing that, we need to first create a transaction, like always. Then we need to create our index dictionary. So we use a skip list dictionary for that in the example. And here you see, so max level is for the skip list of how many levels it has to do the search. So it has something to do with how many pages does it need to iterate, or if it can find it faster. But we need to set the key size here explicitly. And for our example, I just put it to 16. So that means our keys are now 16 bytes long that we store in the index. And all the names just converted into a number fit very well into that. And then we actually, in this example, that's why we put the dictionary as the root. We put the power index into the root. And this way we have then the index pre-configured, and now we need to fill it. So filling the index, we do by just iterating once over all our heroes and adding in the index, add the name, we put the hero, and this way our index is set up to be used. And I will show that in the image. So we are now here, so we create again our transaction, then we create our index, we put it there, and then I think my window is too large. Now we walk over, we fill our index by going over all heroes, and we commit. And now our database has the normal data, and it has the index in the database. And we can now reopen it, and it is in the correct state. And that means if we make a new transaction, we can now say tx root@power index, add regeneration. There should be a hero that actually does that. So let's actually look at that. And if we do that, we get Wolverine, which has that power. And that means that we do not need to load the whole model to find the hero that implements this in this power. In our example, because it's just an array, it would have loaded. Oh, no, it would not, because it did not load all the heroes, because that's lazily loaded. We didn't access it, so we really just load the one hero from disk, and the other one stays, and it's not in the image. And as we didn't change anything, we can abort the transaction, and we are done. So that is indexing as we have implemented it until now. This is the index lookup. We saw that already. I want to show a little bit more things that Soil has. One thing that we implemented is backup, so you can actually programmatically create a backup of your database with just Soil backup 2, and then you give a file reference, and this copies your database over to a second database, and then you can open it like any other database, and it's a full backup. This is quite useful. In addition, of course, you can back up the files of the database itself, or no. So the backup is then, it creates a backup on disk, and then you can back up that one, the files on disk, to your backup service, and you are secured. That's what I want to say. One thing that is interesting, and often a question that people have, what about if I change my model? So one change that people might do a lot is that the classes that you store, that you change the shape. So that means you add an instance variable, you remove an instance variable, you move an instance variable from the class to a superclass, you add a class in the middle, you remove a class. How does Soil handle that? So Soil actually, the serializer, does not care about offsets at all. It actually uses the, names to store objects. And that means the order of instance variables is completely irrelevant. And it's irrelevant in which, where in the hierarchy the variable is. So that moving variables around is completely transparent. We support removing instance variables, then it loads it and it ignores the data. Data's on disk, but you don't get it in the image. And if you add an instance variable, you get a nil object when you read, of course. Another question is, what if the class, what if I add a class in the middle somewhere, remove things? So we actually always take a flat view. So that means we do not store the class and the superclass. We store a description, which is the name of the class and the flat view of the instance variables. And that means we do not care at all about the class hierarchy. Of course, it loads it into an image with a class hierarchy, but we have the description. This is the name of the class, and it has all these instance variables, which are the instance variables of the whole hierarchy. Another thing that we added is support for class rename. So that means you can tell Soil the old name of, when you rename a class, you can tell it that you did that. And that means that Soil will load the old name into the new class. This is not directly integrated with the deprecation system in Faro because class deprecation, because you might actually want to have that around much longer. So you might already clean up your code in Faro and the deprecation, class deprecation is already gone. And you still, Soil still knows, because you know on disk I still have old classes, and you can continue to load them. And only if you read once and write back, then you could, and you guarantee that you did it for the whole data, then you could remove that and you can clean up. Another evolution support is the application version that you can define. And there, I think Norbert could explain a bit more because he uses that a lot for AptiveGrid to do large transformations.
Okay. Yeah, I mean, we try to be supportive, so it's not about Soil and only we in Soil, because we know usually you have an application that what data you want to store in Soil. So we have a global field for the application version. That means that usually if you want to have an easy migration, which Soil supports right now, is that you have a code version in your some kind of a class method, and then that gets stored in the application header. That means that when you open a database, you can ask it if it needs to migrate, and then it can kick off the migrator to make your own migration scheme. So, not sure if that's understandable, but it's for you. It's a field in the database for you to keep track of your application version, or to say the version of your application model. So, and yeah, the migrator uses it.
So what is the direct next future? I mean, the long-term future we saw a whole talk about. So the direct next future for, I guess, the rest of the year to some extent is, so the next thing we want is duplicated keys, because you have seen that we have a very simplistic dictionary model for the index, where you have one key with one value, but in many, many cases, this is not what an index is about. So imagine you have people and you want to index the last name. Many people have the same last name, so you would like to get all of them. Or the heroes, yeah, two heroes have the same power. You would like to get two heroes back when you ask for the power. And so that's why we are working on actually changing the model of the index to not be a simple dictionary anymore, but to be an index key to multiple values, and with the possibility to even stream the multiple values. So you say, give me the first one or give me the first 10, and then give me the next 10. And so this is much more what you would think of an index in practice. Then mark dirty needs to disappear, so this is on the list. Another idea on the list is multi-indexes, because you might, so if you have a person you want to actually index for first name and last name, and you don't want to do multiple dictionaries, but you would like to have a collection where you put them in, and it knows how to do multiple indexes, or you can define multiple indexes with different features. Bit more midterm, long term is a query builder and planner, because right now it's dictionary. It's like you manually need to use the index, but it would be nice to have a query builder, and then something that actually knows which indexes are there to use them, or suggesting to you which indexes to create. And another thing is better support for objects that are both in the image and the database. That's a bit of, for example, if you start about thinking, oh, I would like to put all compiled methods in the database. How do you do that? So we need to think about objects that live in the image constantly, but are in the database too. How do we manage that? And that's it. So now we have not really that much time for questions and answers. So if you have
If there is any question.
I have one question. For the evolution scenario, because you said, okay, we don't keep the... If I rename an instance variable, what's happened?
If
I rename an instance variable. If I rename...
If you rename an instance variable, so right now we did not implement what we want, but it's the usual stuff in an object. You have 5 versions, and then the intersection, the instance variable that was present in all versions is kept, the rest is thrown away. But the future is that we store the refactorings. So that we store instead renamed instvar. Then when you load and migrate, you can copy the state from the one to the other.
So
So
this
it's
is not
prepared.
yet implemented. So this is on the
Not
to-do
yet.
list, the next thing.
Because for me,
migration.
that's the key things, yes.
Yes.
Yeah.
Yes.
Okay, thanks. Okay.
One of the topics is static data, like preloading a catalog of whatever, your products or something, and having it detached from the database. So, of course, you could read them about the transaction, but how do you avoid reattaching it when you commit the next transaction, which references that object?
That's not possible. So there's two. Well, you can answer. So the transaction is the mapping from an object in the image to an object in the database. If the transaction has gone away, this association is gone. So if you keep a reference to that object in memory, which you shouldn't, and you commit that, it will get a new copy. So there is just, so I'm thinking about, because I use something which I call detached object, that you can make that deliberately, saying, so this is something that should outlive the transaction, where you give a wrapper, you get a wrapper object which remembers which database address it has, and if you're saying reattach, it will bump into with all the troubles you asked for. So meaning that every change in between will be overwritten, yada, yada, yada. But I think everyone should be empowered to do the most stupid things he wants to do. So, you know, small talk. False become true and such.
And then there is a second question. You didn't, you showed this, I want to make this a transient border for not following, for committing that object. So don't follow this instance variable for writing data back to the database. And I was wondering why you didn't choose to use slots for that.
Well, we talked a lot about applying some slot stuff to this, and yeah, not yet. So there is no pressing need to do that. But if you can come up with a good reason, future list. So yeah, we're always talking about that stuff, how to put that stuff, but you know, just because there are slots. Underused feature.
So I think SQL, well, does again SQLite is a single process database. It's not a multi. It's not SQLite is not multi-threaded, I think, or you can only access when it runs in a process of the application, so this runs in one image. How it's stored on disk? So how would several images talk to the same database?
Yeah, I'm not sure if it's a good answer. So actually, you shouldn't. So that the code is prepared. I know it's not really working out. So there's two things. So Soil now supports caching of the object segment, which is then per image, but it accelerates everything so much that it will be faster than having multiple images. Multiple image would mean that you have no in-image caching. So you always go to disk and read the pages because that's the only way to sync between images. But that's usually not useful because you just have the page, we have a page cache. So we cache the pages in memory so you don't have to go to disk. And this is 100 to 1,000 times faster. So you won't gain anything by having more images. So if you're up for performance, multiple images will not accelerate it.
In your previous presentation, you demonstrated a kind of communication, a gossip model that actually distributes the workload.
Yeah, but there is the discovery to see the host to find the physical storage of the data. And then there's a gossip for the image to organize which of the images takes this database. So, and our approach is just that we always make sure that only one Faro image has opened that database. So the distribution is about, we have 6,000 databases, and they're distributed among the Faro images, but only one image always has one database. And every Faro image has multiple databases, soil databases. Not sure if that answers your question, but that's mine. Yeah. Come to me, talk later. To us. Thank you.